Good evening, and I'm so sorry not to be with you in person. Entirely my fault for a diary mix-up, and I'm sorry to be missing the champagne and strawberries, but I hope that what I'm going to talk about this evening is highly relevant and highly interesting to a group of people who've spent a long time understanding how materials add value in various applications in society today, and in this case, in energy, which we know needs all the help it can get as we go forward in this century. So this talk is entitled A Materials Roadmap and How It Paves the Way for STEP in North Nottinghamshire. And I'm going to dive in and do about 45 minutes. I hope you can hear me clearly. I can't see you, but at any point in time, if something goes wrong, I'd appreciate somebody just yelling a little loudly. Otherwise, my narrative is as follows. It's to give you a bit of a 101 on fusion this evening, as opposed to fission, and what we mean really these days by fusion, not as a science, but as an engineered reality. And then to talk very specifically about STEP as the exciting way forward for the UK in fusion and what it needs in terms of materials, both new ones and actually the optimization on existing materials, the challenges we face. So off we go, an introduction to fusion. Some of you will have seen that in the press these days, we get lots of attention. And so what an interesting thing to be able to put up a graphic that comes straight from the Sunday Times. We've certainly made it onto the mainstream in the energy sector. We are looking at the moment at the fusing of two hydrogen isotopes, deuterium and tritium. And I say that because fusion can be other isotopes. It doesn't have to be deuterium and tritium, but we've worked out that these two, at this moment in time, give us the greatest amount of energy for the amount of effort we have to put into creating the reaction. And if we fuse those two in a confined space at a very high temperature, we produce an outcome helium, which is a benign gas, and a neutron with very high energy. And it's that neutron with high energy that we actually want to harness. If we feed that through into a breeder environment, which is the little equation at the bottom, putting it into a breeder environment where there is some kind of a lithium substrate, we generate new tritium, which we can feed back into our fusion reaction. So we get a self-sustaining energy source in the long run. But also we get heat, and the heat through the coolants is what moves through to the turbines, as we understand at the moment our power plant to be, and generates electricity. The problem when we do this in generating the neutrons is that we also damage our materials. And so there's more to be said on that in a moment or two. But let me just stop for a moment and say that in order to get the two isotopes to fuse in the first place, so it's the opposite of fission, we're not splitting an atom, we're actually pushing things together to create new atoms. We need to do that in a confined space. And we use magnetic cages at the moment in what we call a tokamak device. So if you're able to see my cursor on screen, this is a standard picture of a tokamak device in which there is a central solenoid or column with a magnet and D-shaped magnets. If you can imagine, we've cut through the orange here and you're seeing a plan view, and the segments of the orange would actually rotate all around the 360. That is the magnetic cage in which we confine a plasma, a ball of burning gas, 150 million degrees Celsius, and in which we therefore feed the deuterium, the tritium to fuse. This creates a lot of engineering complexity for us, but not nearly as much as a stellarator, which is this unusual beast on the right-hand side, where the magnets are set up in such a way as to more formally control what the plasma is doing and rely less on the plasma itself with its induced current to create some of the magnetic field. If we don't use magnetic cages to confine our fusion environment, then we have other spaces. This one, this image over here is from General Fusion, a Canadian company, and they are looking to use a sequence of pistons in a 360 configuration to collapse a liquid metal wall, in this case the lithium breeder that we're talking about here. And that metal wall surrounds an interior in which the fusion reaction takes place. We have other very, very interesting opportunities on the market. These are companies that have spun off, they have venture capital, And one of them is looking at inertial confinement in which a projectile is fired into a fuel capsule or at a fuel capsule. And because of the impact of the projectile, you create a rapidly confining space and a high pressure, high temperature environment, again, in order to ignite that fuel, your two isotopes, to create fusion. So a space in which there are multiple engineering routes, but really at this moment in time, and I apologize, I've hit the button which takes me to the end of the presentation, so I'm going to just quickly roll myself back. You're getting a sneak preview. Almost there. Hit the right button this time. So an engineering reality, and there may be some among you in the audience who go, well, I've read that in the press for a good half of my life or more. Fusion is always 30 years away. And so I think it's useful sometimes to put up this picture on the left-hand side over here. This is a plot of the confinement environment, the sort of pressures and time that you need to confine the isotopes in the plasma against the temperatures at which they're confined. And what you are seeing is a trajectory from lower left to upper right over about the last 30, 40 years in fusion science. All the experiments all over the world that started from things like what we call a Z pinch, where you're just literally using an electric space to control the fusion reaction, all the way through to JET, the Joint European Torus, the biggest tokamak operating in the world right now, sits on the property at Culham, where I was earlier today, through to D3D, an American experiment, through to, if we're talking inertial confinement, the National Ignition Facility in America, and a tokamak that's being built at the moment, Spark in America, by a private company called Commonwealth Fusion Systems. What we're looking for, all of us, is the magic number in Q, that the amount of energy we get out is more than the amount of energy we put in. And if we can hit Q equal to 1, we start to talk about net energy in fusion. And we'd love to get to Q equal to 10. Now, just this past year in the inertial space, the National Ignition Facility in America hit Q equal to 1 and indicated that they'd actually produced more energy than they put in. But they qualified very carefully in the press that they meant that was the energy that they put in through heating for the energy they got out. You've got to still consider the parasitic load or the power that goes into running the laser that produces the heating. And if you take that into consideration, then we're not yet in a net energy space. So we have some way to go, but you can see that the movement is real over the last couple of years. And industry is noticing. So the picture on the right-hand side shows you that from 1992, over the last 30 years, the number of spin-out companies, the number of investment vehicles that have been created, and that this is rapidly ramping up at this moment in time. And in fact, we're looking at over £3 billion worth of investment just in the last few years into fusion. So a space that's very exciting to play in. It's what keeps us all at work, scratching our heads with significant headaches. On the left-hand side of this image, you're seeing the tokamak with the purple space indicating the plasma spinning around with the fusion reaction taking place in that plasma. And what we've got to hope is that the neutrons are released and they move through the walls into a blanket environment. And that blanket environment with some kind of a lithium substrate is where we generate the heat. And we've got to tap that heat off and convert that for our electricity grid. And in the meanwhile, what we're having to think about is, will we, when we react those neutrons with the tritium in this breeder zone, or sorry, with the lithium in this breeder zone, will we generate enough tritium? Or is the tritium going to lock up in the first wall? Or is the plasma simply not going to generate enough fusion to actually burn through the isotopes adequately and produce enough tritium for our inventory? So the tritium fuel cycle is one of our big challenges. We have to exhaust the heat, actually. So we're holding the heat in the middle, but the particles that move to the edge move through a scrape-off layer and down into an exhaust zone, and they have to be removed from the system with a material environment that can handle extreme heat loads. And we talk here about 20 megawatt per meter squared in some instances, a considerable heat load on the walls in the exhaust zone, what we call the diverter zone of the tokamak. And then we have the materials throughout. which are exposed to neutrons, and I'll come on to that, how badly they are damaged. And then we have to think about the power plant and whether we actually produce enough thermal headroom to generate electricity through a turbine system or equivalent. So many challenges to go, not least the control of the plasma itself and whether we can get ourselves to a self-sustaining plasma that doesn't need constant heat fed into it to drive that fusion reaction. Can we get enough heat off of the fusion reaction to drive the plasma forward? We know that this is a multidisciplinary challenge, and so at the UKAEA, which is our national facility for fusion, we've got a tokamak that's been operating for 40 years, and in the press this week you'll have seen that we come to the end of the 40 years at the end of this year, 2023, and JET will close down. It's run deuterium-tritium campaigns in the last year or two as final closing gesture. And not all tokamaks do run full deuterium-tritium. Sometimes they just run deuterium-deuterium, and they're still producing fusion, but not at the level that we've had JET run to do phenomenal science experiments for 40 years. This is a traditional tokamak. It has a shape like a donut. Britain has pioneered an alternative shape here on the left-hand side in the mega-amp spherical tokamak, and that's because we've gone for something that has a more compressed size and shape. It's more like a cord apple, and that's why it's known as a spherical tokamak. It means more heat going through the system, and therefore we've got some really novel diverter or exhausts at top and bottom of the engineering design. But we hope to make a more compressed power plant at the end of the day, and therefore reduce the costs and make fusion more commercially viable. That is the aim of the spherical tokamak. At Culham, we have a materials facility, the research facility where I sit by day. We have hot cells and we can handle radioactive material. We're doing the research to make the kind of materials that coat the walls of this tokamak and help to make them resilient to the heat and the neutrons. The materials that we test are very small because they're radioactive. But if you zoom them up to meter scale components, we're hoping to put them into a rig called Chimera in the next 2 years that we're building through our technology division, where we will apply heat loads, magnetic loads, and thermal loads to try and simulate the multidimensional environment that components find themselves in a tokamak. And that's very important on the route to qualification of materials and components for the eventual regulation of this industry. We have a tritium science capability to work on the fuel inventory, and we have robotics capability because once you've had tritium through this plant, it is radioactive, it's tritiated, and you can't let your labor force in for a couple of years. And so any remote maintenance that you want to do has got to be done through robots and robotic technology. So all over the world, this is the story that is taking off. In Korea, South Korea, we have an experiment called Korea Demo, which aims to build something in engineered space that really walks the path to electricity, not just science. In China this past year, they've had a major tokamak breakthrough where they held their plasma pulsing for long periods of time, 1,000 seconds. If we pulse at JET, we only pulse for about 5 seconds and hold the energy. But the offset here in China is that the temperatures were lower, the energy was lower. In Britain in 2020, we pulled the world together to announce that we were going to build a power plant, not just a tokamak. And that's what I'm going to talk about more this evening, the STEP power plant. And we did that off the back of the knowledge that France is building for the global community the device called ITER. ITER is £20 billion, the world's largest science experiment in Cadarache. It's 80% built. There are some delays. Inevitably, when you do something like this on the scale for the first time ever, there are enormous learnings at very pragmatic levels, like getting the welding right. But if we can see ITER clear to coming on stream in the next decade, it certainly will give a lot of impetus to things like STEP and also the plans in America. I've mentioned the National Ignition Facility that got itself to a very high energy output using inertial confinement, not magnetic confinement. But we also have seen the White House announce a bold decadal vision for fusion in America. And we've seen private companies like Commonwealth Fusion Systems building full tokamak plants at this moment in time. So this is a global story that is emerging, a multi-billion-pound industry with lots of challenges to go. So let's talk about what we're going to do here in Britain. A spherical tokamak aimed particularly towards putting energy onto the grid, at least as a prototype, a small amount of energy onto the grid. We're going to go the magnetic confinement route. So it is a tokamak that we're building. And not only will we try and build this prototype power plant, but we will also try and build the ecosystem around fusion such that when our, I'm going to say if not, I'm going to say when, not if, when our power plant prototype works, there is the possibility to immediately take up commercialization of the prototype to develop a fleet and an industry. So you don't start that overnight. You work many years in advance to set up a regulatory framework, a government policy framework, a supply chain, and all of that is part of the STEP program at the moment, not only the concept and the design and build of the power plant itself. So to show that we are well on our way to doing something real here, the government ran a tender process recently through UKAEA. There were 5 sites down selected in the end, and finally one chosen. It is at the West Burton original power plant site up in Nottinghamshire. And the picture I'm showing you over here shows you the site as we see it now. It has many benefits for a future fusion power plant. There is a train line in existence to bring staff and supplies in. There is a 400 kV grid connection, which will allow us to tap our power straight out to grid. We are able to disperse our coolant into the River Trent with an existing thermal load approved and permitted, and we have an enormous amount of space on site, much of it that still has to be cleaned up. We've got a lot of fly ash from previous work, and we'll try and use some of those recycled materials in the civils build. And STEP will be up as a new generation power plant on the site of what was a traditional coal-fired power plant. And I think there's a wonderful story in that. In order to do that, in the next 12 months, UKAEA, as the Atomic Energy Authority, will spin out a delivery organization called the UK Industrial Fusion Solutions Limited, UKIFS. And this will be its own company driving the STEP program forward over the next 2 decades. It will have 3 big partners: a fusion science partner, which will remain the UK Atomic Energy Authority, but it will also bring in a construction partner to start the civils and an engineering partner to start the plant design in its true final engineering form and to do the plant build. These are likely to be consortia of tier 1 integrators, major players in the fission world, but also beyond the fission and existing nuclear world. And then there will be all sorts of specialist partners in the supply chain to bring in very unique elements of the build. So you can see from what I'm showing you that we have a site and we have a structure in the business space. The government has already issued a regulatory paper and a policy, a national policy on fusion. All of the pieces are there for a fusion future in Britain. And in fact, by constructing that context, we lead the way. America has turned to us and recently put out their decadal vision and changed their regulatory aspirations. And Europe is looking to what we're doing and starting to update their roadmap because they have a power plant planned for 2050 called DEMO. So we are leaders here. We should be very proud of that. If we look at the exact timeline for STEP, we have spent the last 3 years and we have another year to go in the tranche 1 phase, developing the concept of the full plant. And that plant concept maturity is run using a scheme that NASA uses, concept maturity levels CML 1 to 6. We'll reach CML 5 in September this year, and CML 6 we hope by the time we spin out UKIFS in the first half of next year. As we work as a team of about 200 people on the program, and that's the STEP program itself, that's not even pulling in all of the partners from robotics, materials, technology, and tritium. We are working on iterating the concept. And by concept, we mean the plasma shape, its edge, its size, what type of magnetic conductors are in the magnetic cage, what the coolant inlet and outlet temperatures are, what the magnetic field needs to be, how much parasitic load we can get away with before we actually lose any net energy in the design. And we iterate in double digits for each of the concepts as we move through. So there's an awful lot of work going on, combing through the knots to get ourselves to something that we feel we could pass in 2024 into the tranche 2 phase, which is the detailed design. And this is where we start with the early manufacture of long lead time items, and we're eventually moving into the early 2030s, we move into the actual plant manufacture itself. And we hope by early 2040s to be commissioning our operations. What we will have as we go through the commissioning of operations are a number of phases where we start just putting pure hydrogen into the plasma and seeing if that will work, then going to deuterium, and then ramping up eventually to tritium. And while we've got a couple of dates here on the side or indicating how long it might take to ramp up, I was asked to be very clear on the caveats of the timings and say that these have as yet not been formalized through UK Gov. But it does give you an idea that there is a sequential boot up that happens as we reach our maximum operational temperatures, as we demonstrate that we can work fully remotely, as we get to the first plasma NDT, as we get to first net energy, and then close the fuel cycle so that we're not having to add extra tritium in, and finally get to continuous power. So this is what our STEP program looks like through the years. And now I'm going to move us into materials and say, why all the fuss? Well, the fuss comes from a variety of angles at us. Neutrons are like the cue on a billiard table, and when they come in and make contact with the atoms in our materials, they scatter them like the balls on a billiard or a snooker table. And we call that displacement. What is actually happening in this little diagram over here is that an atom will move out of its traditional place in the lattice, and it will sit in a space that it shouldn't ordinarily be in, and we call it an interstitial then, and it will leave behind a gap, which we call a vacancy. And each one of these interstitial and vacancy pairs we call a Frankel pair. And as they knock each other, there is a knock-on effect, and you can build from a point defect to a dislocation, a line defect. And those can aggregate and move towards grain boundaries in the materials, and you start to see bigger defects. And we see voids, and we see cavitation, or we see changes in the dimensions and the volume of the material, and we see swelling. And all of these things have been really well documented by an excellent Professor Stephen Zinkel in America at Oak Ridge National Lab, who has led the way internationally on this understanding of the variety of phenomena we would see as a result of neutron imposed displacement in materials. We have at the same time the fact that some of our materials will experience neutron capture and decay. There are a variety of neutronic reactions that are underway when you put the materials in proximity to the neutrons. And the example here on the right-hand side shows you that if you are moving across the radionuclide chart, you might take something that is uranium and change it into neptunium and change it into plutonium. And then with a little bit of decay, you move up the plutonium isotopes, and then you have another capture and decay, and you move across to americium. And so this is an example of a transmutation sequence in beryllium. And beryllium actually is the first wall material in our JET tokamak on campus. Or it's rather, I should say, it's a uranium impurity, a small portion within the beryllium first wall in the JET tokamak. So we have to be mindful that if we coat our tokamak in step with something like tungsten, which is the preferred material at the moment, then the tungsten can transmutate into rhenium, and then from rhenium into osmium. And as you change the composition of the material, you're also changing its properties. And so these two, the displacement quite immediately and the transmutation over time, will also interplay with one another to give us a fairly unknown and quite experimental environment for material science. Like those of you who might have been or are involved in space research, materials for space, we're dealing with an environment that we can't emulate on Earth right now. Makes it very difficult to do the test work to prove the materials. We also know that our materials, by virtue of the fact that they get damaged, will create trap sites, both at micro and macro level for the tritium fuel and the deuterium fuel. And so we do a lot of work at the moment to understand what the mechanistic trapping looks like in our materials. This is for tungsten, our first wall tungsten material. And what we've got here is deuterium atoms, which are being released after having been trapped in the tungsten through heating of the tungsten. And we can see discrete peaks, which tell us that there are specific energies attached to certain trap sites. And therefore, the more we understand about the material and how it's damaged, the more we will understand how it locks up or releases the tritium fuel. So this is the story of the Fusion Materials Challenge. And to really bring it home to you, these examples to me are very powerful. They're all from published literature, and each of them is a metal or an alloy. We've got copper, chrome, zirc alloy in this picture in the middle over here. We've got a titanium, aluminium, vanadium alloy over here. There's standard Inconel over here. Each of these has a graph line which shows you unirradiated performance in a standard engineering environment, a stress strain curve. But after we've applied a little bit of fusion damage, and we measure it as displacements per atom, DPA is the metric, and even these low levels of DPA considerably reduce the performance at a mechanical level of what we hope will be standard building blocks in the tokamak. And you can see the pattern is the same across all of the pictures. So we see even after a couple of days of full power on step, we anticipate major modification of the engineering performance or behavior of our materials. You might look at that last slide and go, well, that looks like a really bad game to be in. Is there any hope? And there is some hope. So this picture is all about saying, let's put it in perspective. We've done some phenomenal modeling over the years where we look at the DPA, the displacements per atom, the amount of damage in a year of operation from the first wall with depth away from the first wall through the plant or through the tokamak to begin with. And what you'll see is that actually the damage drops off fairly radically once you get away from the first wall. So it is the first wall where we have to concentrate most, and in the breeder zone. When we get back into the magnet shielding and the vacuum vessel, then we have less of a problem on our hands. The other thing that I can say to you is that we do know that the damage saturates. And so this image over here on the right-hand side is showing on a stress curve, so this is an engineering curve for displacement damage, that eventually some of the performance does plateau out. And so we see the temperature anneals some of the damage, and we see some of those damaged sites recombining and therefore healing themselves. But to show you how much of a jump we're at, this graph down the bottom end, and it is really just a draft at this moment because we don't have all the neutron wall load statistics in yet. Depending on how STEP is designed, it will modify. But if we think the jet has been built in recent years, and just looking at the last couple of years on the timeline below, the neutron load, the fluids, the total load on the wall is in the order of 10 to the 15 over here, neutrons per square centimeter. ITER will look to put a load at orders of magnitude higher fluence. And then if we look at the blue lines as the bracket for STEP and eventually demo the European power plant, you can see that we're into a domain of neutron load that is significantly more onerous than what we've ever tested in experiments in real tokamaks to date. And so that is the work, the burden of proof that lies ahead of us. And that is why a year ago, with about 100 folks representing 40% industry, 40% academia, and about 20% parastatal, other national labs, we came together to create a roadmap for fusion for the UK. And what we were saying is, because we're looking at magnetic confinement, the materials are going to have to work in magnet environments which are cryo-cooled. Because we are working with tritium fuel, we're going to have to think of ways to boost how that fuel moves through the plant, but at the same time is blocked from actually entering things like water coolants, where we don't want radiolysis of the water and we don't want the tritium moving beyond the safety controls of the plant. We've had to think about the fact that at the moment, the best steels we've got globally in fission or fusion max out at about 550 Celsius as structural materials. The creep after that makes them unsuitable. And if we really want this to be a power plant and we want thermal headroom on the power plant, then we really need that temperature much higher. So can we lift the structural top temperature? These are very niche developments: better magnets, better tritium barriers, better structural materials. Globally, there are other roadmaps, and Europe has had one out for a good decade where they've talked about better high heat flow materials, better first wall armor materials. So what we try to do with the UK roadmap is to push some of the complementary and more niche fields that need to be looked at alongside what's already been considered globally. Across the piece, why we find ourselves in a different space to Europe and others perhaps is because we're moving quite fast towards that power plant, and we need to move beyond science into engineering assurance. We need regulators and design engineers to know how the materials will behave once we turn on the switch. And so we've got to somehow predict routes to failure, even as we can't emulate this power plant. And so I'll come on a little bit to predictive modeling and why we're doing so much in predictive modeling. And then finally, the better we are at the compositions of the materials, removing those elements that really transmutate badly, the less activation we build into the plant and the lower the waste classification and categories eventually for the fusion materials that we must dispose of. Fusion at this moment in time aims to have no high level radioactive waste, minimal or as much as we can reduce the intermediate level waste, and then obviously there will be low level waste. And so this slide is a prop to the conversation. It's not for reading or going through out loud here, but really just saying to you that against those 5 themes in the materials roadmap, we have some very specific targets in the near term, which we hope will help us to build STEP, but we also hope for some disruptive technologies going forward. And we've hoped and engaged with the academic community to say, come and join us alongside industry in pushing the boundaries of materials, because better materials make for an easier engineering design at the end of the day. So I said to you just a little while ago that STEP is both the building of the prototype power plant, but it's also making a commercial ecosystem viable. And for the prototype, we are selecting baseline materials at the moment, building a property database and looking at how we can do predictive modeling. But at the same time, for the future fusion capability, we are trying to develop new materials and validate our models in other spaces. So let's move then to my last of my 4 chapters here to talk about existing materials and some of the challenges we face. We've got some fusion steels, you'll be glad to hear. We break them into maybe 2 big families. On the one hand, we're trying to reduce their activation, as I mentioned, and we talk about roughened steels, reduced activation ferritic martensitics. And actually, we have 2 that are known across the world: Eurofer, cast in ton scales at this moment in time in Europe, and we have F82H cast in ton scales in Japan. And so we have a RAFM. We could just do with that RAFM being even better in terms of its temperatures, and we'd like to crack through that 550 barrier. And we need to make tens of tons and start to show that we have a realistic supply chain. And we need to be able to weld these materials. So there's a lot of research going into how we join steel to steel and steel to other materials. At the same time, we not only need to reduce the activation, we've got to improve the neutron resilience and improve that creep resilience. And we're doing that at the moment through the creation of precipitates, secondary phases inside the steels. They are sometimes oxides, and we talk about oxide dispersion strengthened steels as a standard nomenclature, ODS steels across fusion, but increasingly these days also about other nanostructured alloys that might be cast, where the ODS are often powder metallurgy. These are more cast, and they may have carbide precipitates in them. So there's a field of work to see if we can use secondary phases to improve these steels. So I'm going to dive into that just briefly and say to you that if we take the internal structure of a RAFM and we know that we have prior austenitic boundaries, we'd like to introduce these precipitates on the boundaries, but also inside the grains, so that we have the precipitates act as defect sinks when we get dislocations running through the material from the neutron displacement. But we also want them to be mopping up the gases that are generated through the transmutation reactions. So they act as both defect sinks and they act as gas moppers. And you can see here that as we take the temperature up, the creep performance over creep lifetime is reduced. And this work is from Michael Reith, one of the foremost scientists in fusion metals in the Eurofusion program in Europe. And you can see the rapid drop off here at the moment above 550, where the existing precipitates are becoming unstable, and therefore we cannot at the moment take our Eurofer beyond 550. So what we've tried to do is say, can we improve on a conventional RAFM with an advanced RAFM by applying new compositions and improved thermomechanical treatments and get ourselves to something of higher temperature? Can we increase the number of precipitates, decrease their size, increase their density, and see if we can get ourselves to something more optimal? And we do believe that we could get ourselves to 650. Both applying research in the RAFM area and the ODS area, and we have programs in both. But if I just show you on the RAFMs for now, working with Swansea, we've worked with ideas that come from the literature. We can't claim total novelty, where we're trying to heat our RAFM steel up into the austenitic phase and hot roll it there to introduce extra dislocations, so that once we anneal, we have extra nucleation sites for those precipitates, and we then have novel quench temper sequences to lock in those precipitate phases so that we can get ourselves to better defect sinks. And so we ask ourselves, did we create the microstructure we targeted, and is it stable against ion irradiation? And in the first instance, under microscope, we're happy that we have managed to generate something akin to our theory. And there is a lot of high resolution SEM and now TEM work coming on stream at Culham, the Materials Research Facility, on irradiated RAFMs. And if we slice using focused ion beam, FIB, to get ourselves to thin foil pieces of these steels, and we look at them at those type of scales, these are in nanometers, we can see that we are producing networks of damage cascades from irradiation of the steels, but we also have the kind of precipitates, large and small, that we want in place in creating these RAFM steels. This is just another slide to say to you that we have, relative to the conventional RAFM, markedly improved the density of the precipitates in the new advanced RAFM generated last year at Swansea. And we're working with the crowd under Professor Cameron Pladle-Pierce there, and I acknowledge the work of that team here. Our next step was then to take some of those samples and irradiate them at the Surrey Ion Beam Centre at the accelerator there, and see if we could push in 100 displacements per atom, a considerable amount of damage at a very high rate of damage, up at 600 Celsius. This is the kind of operating temperature we're now pushing for, and see what happens to those materials. And what we can see is in a profile, and here is the surface of the material, and this is the depth down into the material, and this is the DPA profile superposed. And what you can see there, rotated and expanded, is that we've lost our precipitates in that very high damage zone in our first results. So the importance, I think, always in presenting a discussion on research is to highlight, particularly perhaps to people who are new to research, that research doesn't always give you successes. It gives you a no before it gives you a yes. And what we've had to say to ourselves is our nanoprecipitates are indeed unstable during the irradiation, but at the same time, we know that we've punched in that damage at a very high rate and very high degree. And if we did the damage imposition at a slower rate and to a more incremental degree, and allowed for some of that annealing I spoke about earlier and that self-healing, would we still see the situation that we see at the moment? So this is a very first result, and it comes from an ion irradiation and not a neutron irradiation. So what we want to make sure going forward is that we iterate this work and we see if we get something a little better. We've also taken things up to higher magnifications, and we've started to look at the chemistry here to understand how mechanistically we are losing the precipitates. So there's a lot done on understanding what the irradiation is doing to the chemistry and what is causing the instability. And with that in mind, I'll switch just briefly to the other steels. I mentioned the oxide dispersion strengthened steels because these really show a lot of promise if we can get them to work. The data on the left-hand side here is unirradiated data, but you can see how much better in a stressed environment at the temperatures we're interested in, the ODS performs relative to the RAFM if we can preserve that relationship post-irradiation. So we're using yttria as the primary oxide dispersant, and we've exposed some of those samples to irradiation. And one of the things we know is that if we use a self-ion irradiation, we do not see the generation of an alpha prime phase, which means the segregation of chrome in these chrome-based steels. Whereas if we actually go to something like the BR2 reactor overseas, which is a neutron reactor, at the same temperature and for virtually the same degree of damage, and for an identical composition, we can see the chrome segregating out in what we call the alpha prime phase. What is tricky for us is on the phase diagrams that exist today, the solubility line, which takes us into the alpha prime phase, is very dependent on which of the scientists and which of the papers in literature you're looking at. And so if we could get some better handle on that solubility line, we'd understand a little bit more about how we might minutely control our composition so as to reduce the triggering of the alpha prime and the segregation of the chrome, because it's that segregation that is immediately harming the mechanical properties of the materials. And so I will end really with two quick last punchlines. The one is to say, you should always have plan B. If steel doesn't work, can we use ceramic composite? And in the same way that you've just seen me talk about artificially loading samples up with the effects of fusion, we're trying to do the same thing with silicon carbide ceramics, where we're loading them up, not just with damage in DPA, but we're loading them up with proxies for transmutation. We're actually putting other materials or other elements in and pretending that we have transmutation and generating the gases that we need to start to study the microstructural effects. And so we're emulating 5 years of first wall lifetime. We're having a look at how transmutation burns up the carbon part of the silicon carbide stoichiometry, so how the material is actually changing in terms of composition, what defects are arising, and actually if we put this alongside a liquid breeder, would the corrosion from the liquid breeder lithium cause damage as well? We know it does with the steels. We are also evaluating now with the ceramic composites. So just touching on these slides, and I hope towards the end, I'm sort of ramping up the detail here on the technical side. The idea is to sort of be like a firework display and say, look at the proliferation of exciting work that is emerging just in the last 12 to 18 months. And just through one center, this work that I'm putting up in front of you now is a series of little needles, nanoscale needles that have been cut through one section of a piece of tungsten to have a look at what our first wall might be doing to trap the tritium. And we're looking at those tiny needles on atom probe tomography, and we're picking up from the segregation of things like the phosphorus and the nickel, where the grain boundaries are, and we're looking to see if our deuterium is trapped along the grain boundaries and whether it's associated with some of the tungsten oxide phases. So we're beginning to pull not only the impact of the microstructure on damage resilience, but also the impact of the microstructure on the tritium trapping. And you recall a couple of minutes ago, I said to you, tritium, transmutation, and displacement. So lots of new work coming out at the moment. And I've talked about steels and ceramics, and I've talked about tungsten, which in my head straddles the two because it's a metal, but it's sintered like a ceramic. And at the same time, what we have to do in order to be able to do all this wonderful materials development and proving is we have to have techniques development. And so what you're seeing in that little video up there is a fantastic high-res image of just one fiber of silicon carbide becoming debonded and sheared away from its surrounding matrix in a silicon carbide composite. and starting to look at the size of sample that we might use and the strain gauge lengths and what the results are in tests such as this one, debonding, but also microcantilevers that have been cut using focused ion beam. And in stress strain fields are showing us that we are getting modified behavior, but not so modified that we can't still think about these materials for fusion. So a bit of steels, a bit of ceramics, a bit of tritium, and a bit of technique, all thrown in there to highlight where the material science is going. We want to take the data that comes off of the work I've just shown you and put it into modeling, not at the atomistic level, where solid state physicists have been working for a while, and not up at the finite element model level that the engineers work at. This has been done. There will be more of it. We do need to do it, but we most of all need to work in this space over here, the mesoscale space. And my analogy that I've used before in public talks is to say, we're inside the brick here. We've pushed the wall over there. How are the bricks and mortar behaving with each other here in the middle? This is where the wall really breaks. And so this is the modeling we're trying to do using some very clever ideas from academia, but also from industry. We are taking we're taking materials at polygranular level. So you're seeing multiple grains in this image, and we're irradiating them with small levels of damage over here. And we see typical phenomena of slip bands being created in the material. And we are able to pick that up in real life using digital image correlation, where we actually at high resolution pick up the pictures under the microscope. And then we're emulating unirradiated and irradiated using our simulations, so digital space. And we're getting, I think, pretty good replication. It's early days. This is work on Zirc alloy from the fission industry, done as part of a major consortium of work, Midas. So I acknowledge the Midas team here. But saying to you that things like high resolution digital image correlation is a hardware development alongside the simulations which are coming from software development, and that the two in tandem allow us to do some theory development around predicting based on physics laws the modification of the material in the future. So we are working with algorithms where each of the terms represents something like strain hardening, irradiation hardening coming from the neutron impact. And we are validating these terms through small micromechanical experiments. And we're doing this for one slip system and then another slip system. And then we've created solvers to combine the slip systems. And we've created software to produce three-dimensional microstructural proxies, so that we can start to say, yes, we could actually predict that that will move to that with that amount of damage. Now, this is a major body of work, and we have maybe half a dozen folks working on this project at the moment. Britain needs 10 times this number of people and projects. And so I want to lift that one and say to you that sometimes digital is quite frightening, especially those who've been in the industry for decades in nuclear. It's better to see hard experimental fact in front of you. But if we're going to make fusion a reality in a reasonable time period, we're going to have to look to use the digital assistance. And so I end with this slide over here to invite you, if you are in the industry and you are working in materials development or assurance, to come and visit me at the UKAEA's Materials Research Facility at Culham, where we have robotized the transfer of materials from storage castles into working analytical kit in a building that houses a good dozen of these instruments, and which is non-licensed, so you can get yourself to medium levels of radioactivity beyond what a university can manage, not quite what Sellafield can manage, but enough to do some really good work on developing new fusion samples and the techniques to prove those samples. And with that, I will end.